transform the static forms of the gas laws, we must initially posit that the symbols of each magnitude present herein, such as pressure or volume, assume their ultimate form. Meanwhile, the initial form is denoted by the symbol 0. Thus, P sub 0 is interpreted as the initial pressure. The axiom to which we adhere maintains that constancy remains unwavering amidst the initial and final states, thereby permitting us to divide the final state by the initial. For instance, taking the law of Charles, and designating the final volume as V, we proceed to divide it by the initial volume, denoted as V sub 0. The constant divides by itself and thus cancels out, whereas the final temperature divides by the initial temperature. This direct derivation yields the law, often elegantly represented with all initial values juxtaposed on one side and the final values on the other. Considering Gay-Lussac's law, we select the final pressure as P and move to divide it by the initial pressure, symbolized as P sub 0. The constant remains unaltered as it divides itself, leading to its annulment. Simultaneously, the final temperature finds division by the initial temperature. This straightforward deduction unveils the law, typically portrayed with the aggregation of all initial parameters on one facet and the ultimate variables on the opposing facet. Likewise, in the case of Avogadro's law, taking the final volume denoted as V and dividing it by the initial volume, marked as V sub 0, results in the constant maintaining its unchanging nature as it divides into itself, thus nullifying. Similarly, the final quantity of substance divides by the initial quantity. This direct inference brings to light the law, conventionally depicted with all initial qualities aligned together on one side, and the final attributes on the opposite side. Similarly, regarding Boyle's law, by designating the final volume as V and dividing it by the initial volume represented as V sub 0, the constancy retains its consistent nature, self-dividing and subsequently eliminating itself. Concurrently, the final pressure divides by the initial pressure. This immediate derivation reveals the law, often elegantly exhibited with the integration of all initial characteristics juxtaposed on one plane and the concluding traits on the opposing plane. Due to the inverse nature of Boyle's law, we can imbue it with a distinctive interpretation. As the final pressure already involves division, we have substituted the initial pressure, P sub 0, by means of multiplication. Thereafter, it is a matter of eloquently expressing it, aligning the initial values gracefully on one aspect and the ultimate values on the opposing aspect. The same principle holds true for the derived forms as well as for the complete equation of state. This applies to each final term, final volume, final pressure, final quantity of substance, and final temperature, where division by their respective initial counterparts leads to the cancellation of the constant R. Consequently, the equation of state materializes, depicting the transition between two distinct gas states, elegantly and succinctly. Although these techniques might not be commonly found in textbooks, as they represent mere algebraic tricks, they prove invaluable when engaging in profound scenario analysis. They also help circumvent the necessity of memorizing numerous equations. With this approach, one need only commit the equation of state, PV equals nRT, to memory, and then apply the appropriate modifications, assuming suitable constants and state changes as required. Armed with this understanding, we become adept at solving problems using pen and paper. That concludes our discussion for now. If you enjoyed the video, please consider subscribing, giving it a thumbs up, and sharing. Your engagement keeps this channel alive. Until next time, take care.